Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 4, Lesson 4, where I'm going to talk about Kirchoff's rules and then do an example problem to demonstrate them. So Kirchoff was this dude, and he had two rules for looking at circuits. And one of them had to do with a junction, and the other had to do with a loop. So a junction rule and a loop rule. In a circuit, there's usually a battery, and a circuit could be really simple, or it could have different parts. And maybe there will be some resistors or light bulbs or something. In this circuit, these places where I'm putting dots are called junctions. And a junction is a place where current could split or come together. So the current's traveling around, and then it could split and go one of two ways. And Kirchoff's junction rule says that this current into the junction is equal to the current out of the junction. And then the current continues and could go into this junction here. This current would continue and go into the junction here. And they come together and go out. So you get the same information from this junction as this junction. But the junction rule says the current in equals the current out. The junction rule here says the current in equals the current out. So you could say something like the sum of all the currents into a junction is equal to the sum of all the currents out of a junction. For a loop, this circuit would have two loops. I could do what I would call the bottom loop, or in another color, I could do what I call the outer loop. There isn't a top loop. The reason there's not a top loop is if I try to go counterclockwise, oops, I'm going the wrong direction here. You see how the current goes left and I'm trying to go right? Or if I try to go clockwise, okay, I'm going the right direction, but oh, here I'm going the wrong direction according to the arrows I drew. So there's a bottom loop and an outer loop. I would not talk about the top loop because I'd be going the wrong direction for part of it. And Kirchoff's loop rule says the sum, not S-O-M-E, but the S-U-M, of all the potential changes. The voltages. The sum of all the potential changes going around a loop is 0. In other words, what I said before, if I start here and I end here, the sum of all the changes is 0. The junction rule said this sum of all currents into a junction is sometimes abbreviated JXN, is equal to the sum of all currents out of a junction. Ta-da! So those are the two rules. And I'm going to demonstrate them to you by working through this problem. So here's a circuit. Let's look at what's there. Pardon me. There's two batteries. I hinted last time about problems with two batteries. And there's 1, 2, 3, 4, 5 resistors, 8, 1, 5, 3, and 1 ohms. So these batteries tend to make current go through them in this direction. And then they come together at this junction. And so these two currents probably come together and give me this other current. And then at this junction, those currents would split. So let's see if we can solve this problem using the loop rule and the junction rule. The loop rule and the junction rule, the loop rule and the junction rule, Kirchoff's two rules. So the first thing I'm going to do is I'm going to make some definitions. I'm going to call this current I1. I don't know how many amps that is. Hopefully I1 will be in an equation and I can solve that equation and find, oh, I1 equals number. Yay. And I'm going to call this current I2. That's not very legible, but it says I2. And so if I want to solve for those two things, I'm probably going to need a couple different equations. Now, how do I know that these currents both go in the direction that I'm guessing? If I solve and I1 and I2 are both positive numbers, I guessed right. Now, what if, this were, instead of a 12-volt battery, what if it were a 12 million volt battery? Then that current that it creates might be so much that it actually forced the current this way. How do I know? I just set up the things, and if I solve and it says, oh, I2 is negative 7 amps. Oh, that means the current actually goes that way. That's all. So let's see what happens. So I've got I1 and I2, and then I can call this current over here I3. I'd like to know that current as well, and I've guessed that it goes this direction. So now I'm ready to write a Kirchoff's junction rule for here. You should probably press pause for a moment and see if you can write a Kirchoff's junction rule. The sum of all the currents into the junction is equal to the sum of all the currents out. So press pause, see if you can get it. And welcome back. The currents in are 1 and 2. And the sum of all the currents out is just I3. Did you get that equation? Good for you. Now let me get a little post-it, because what I'm going to write next is not important. So I want to be able to write it and then throw it away. What if I looked at this junction? Well, the current in is I3. And the currents out are I1 and I2. And it turns out that that does not give me any more information. This information is identical to this information. I just switched the left and the right. A equals B, then B equals A. I think we called that the symmetric property of equality. Is that right? The symmetric property? You don't need to know that. It's just something that popped into my head. So if you wrote that extra equation, that's fine, but it doesn't do us any good. So there's one equation. Then I'm going to need a loop. And actually, I'm going to need 2 loop rule equations. Remember the loop rule? The sum of all the potential changes going around a loop is 0. And the reason I know I'm going to need 2 is, look, 1, 2, 3 variables. So I'm going to need 3 equations. So I've got 1 junction equation, and I'm going to need 2 loop equations. Now, there's this left space, there's this right space, and there's this whole outside space. Based on what I said last time about, going the right direction or the wrong direction, I want you to think about it. Am I going to talk about the left loop and the right loop? Or am I going to talk about the left loop and the outer loop? Or am I going to talk about the right loop and the outer loop? 2 of those I can talk about where I'm following the arrows. So think about it for a moment. Maybe press pause while you think, and then I'll tell you the answer. Okay, so the answer is the outer loop works. Because see how, as I'm doing this, I'm always going the direction indicated by these green arrows. Going up like this green arrow here. Good. Going down like this green arrow. So the outer loop works and the left loop works. See how I'm going up, following the arrow, down, following the arrow. So I'm going to write an equation for the outer loop and an equation for the left loop. I'm not going to write an equation for the right loop, because if I go clockwise, oh, this works, but oh, now I'm going the wrong direction. If I go counterclockwise, this works, but oh, now I'm going the wrong direction. So I'm going to do an outer loop equation and I'm going to do a left loop equation. I always like to start here on the negative end of the battery. So outer first, 12 volts minus, I don't know this potential difference. I don't know how many volts this is, but V equals IR. Remember V equals IR? Oh, let me get out my Post-its again. So V equals IR. That means the potential difference across a resistor equals the current through the resistor times the resistance of the resistor. V equals IR is about a resistor. So that means V is I, which here is I1, times R, which is 1 ohm. Minus this potential difference, which is IR, minus I, it's still I1, times R, which is 3. I'm doing the outer loop, so I go this way, minus I, which is now I3, times 8. And I get back where I started, so that equals 0. So I have 1, 2, 3, 4 places where the potential changes. An increase across the battery, decrease, decrease, decrease. This is V equals IR, V equals IR, V equals IR. For my left loop, I'm again going to start on the negative end of a battery. This time I'm going to increase 4 volts. And I'm going to minus I2 times R minus I2 again times R minus I3 times 8 equals 0. So now I have 1, 2, 3 equations, and I have 3 unknowns, I1, I2, and I3. So mathematically, it is trivial. 3 equations, 3 unknowns, we're done. But let's go ahead and solve for I1 and I2 and I3. So this equation contains I1 and I3. This equation contains I2 and I3. And this equation contains I1 and I2 and I3. So why don't I just get, instead of I3 down here, I'm going to write I1 plus I2. And then these equations will each contain I1 and I2. Do you see it? So I'm going to change color. 12 minus I1 times 1. That's just I1. This is 1I1 and 3I1. That's 4I1. 4I1. 1I1 and 3I1 is 4I1. Minus 8I3, I1 plus I2 equals 0. 4 minus, this is 1I2 and 5I2, that's 6I2, minus 8 times I3, which is I1 plus I2, equals 0. And then I can further simplify in a third equation. Here I've got minus 4I1 minus 8I1, that's actually 12I1. I've got 12 minus 12I1 minus 8I2 equals 0. Minus 8I1 minus 4I1 minus 12I1 minus 8I2. Here I have 4 minus 6 and 8 is 14I2 minus 8I2 equals 0. And these two equations, this has I1 and I2, this has I1 and I2. And let me write them a little closer to each other over here. 12 minus 12I1 minus 8I2 equals 0. This says 4 minus 14I2 I might have made a mistake here. I'm checking my work. This is an I2, this is an I2, this is an I2. 5 and 1 is 6I2. Do you see how I added the 6i2 and the 8i1 and got 14? Naughty Davy. Oh my goodness gracious. See what I did? I added the 8i1 and 6i2 and got 14, but I combined not like variables. I should have done 4 minus 6i2 and 8i2. Oh, it looks like I got lucky. 6i2 and 8i2. Good. But I had them in the wrong order. I wanted to put I1 first. 4 minus 8i1 minus 6 and 8i2 minus 14i2 equals 0. I just wanted my I1 first and my I2 second. And you'll see why in a second. 4 minus 8i1 minus 8i1 minus 14i2 equals 0. Okay. Things are just more nicely lined up here. I've got the constants and the I1s, and I've got the I2s. So solving two equations for two unknowns. One way of doing that is taking a whole equation and multiplying both sides by some number. And what I see is 8 times 1.5 is 12. So if I multiply everything here, this, and this by 1.5, in fact, if I multiply by negative 1.5, look what happens. Negative 1.5 times 4 is negative 6. Negative 1.5 times negative 8 is positive 12. And negative 1.5 times negative 14 is positive 21. I2. And now if I take this equation and this equation and I add them, the negative 12i1 and positive 12i1 add up to 0. So I1 disappears from my equation. So 12 plus negative 6 is 6. Negative 12 plus positive 12 is 0. And 21 minus 8 is 13. Plus 13i2 equals 0. Oh, that's fun. 13i2 equals negative 6. I2 equals negative 6/13 amps. Hey, look at that. It says that I2 is negative. That means that the current doesn't actually go this way. It goes this way. So my final answer is, the current goes this way, 6/13 of an amp. Now that I know that, I can take this number, negative 6/13, plug it back in to this equation and find I1, and then plug it into this equation and find I3. So let's do that really bigly. So I want to show it so that I can actually see the work. Everything's getting a little small here. 12 minus 12i1 minus 8i2. 12 minus 12i1 minus 8i2. 12 minus 12i1 minus 8i2 equals 0. And I2 is negative 6/13. 12 minus 12i1 minus 8i2 equals 0. I2, negative 6/13. Goodness gracious. Not a very pretty number, but that's okay. 8 times 6 is 48. Negative times negative is positive. So that's plus 48/13. 12 minus 12i1. So I'm going to take the 12i1 and put it on the right and make it positive. And then I've got 12 plus 48/13. Okay, that is, let's see, 48/13 is 3 and 9/13. So that's 15 and 9/13. Is that right? 12. 13 times 3 is 39 with 9 left over. Yes. 12 plus 3 is 15. Good. And then I'm going to divide both sides by 12. And I get I1 equals 15 and 9/13 divided by 12. Goodness gracious. 15 and 9/13. 15, 9/13 divided by 12 is 1.3. I1 equals 1.3 amps. And so I1 is 1.3 amps. I2 is negative 6/13. And that'll give me I3. So I've got the 1.3, and I'm going to subtract 6/13, and I get 0.84. I3, 0.84 amps. Ta-da! So we've used the junction rule and the loop rule to solve this problem. One tiny moment. Let me press pause. I'm back. So again, we learned Kirchoff's two rules about junctions and loops. And I demonstrated the junction rule with this equation and the loop rule with these two loop equations, the outer loop and the left loop. And then we also had some fun with multiple batteries. And sometimes it feels like, oh, this battery is going to make the current go this way. So you write your equations assuming that. And if you find a current that turns out to be a negative number, it just means, oh, nope, the current goes the other way. Okie dokie, that's all I have for you today. Have a great day. Don't break the laws of physics.